So our next speaker is Jack Romeo. Am I saying that right?
Jack Romo.
Jack Romo.
Yeah.
He will speak to us on constructing homotopy bicategories of complete twofold Segal spaces. Take it away.
All right. Yeah, so thank you very much. And thanks to all the organizers for setting up this awesome conference. I've really enjoyed pretty much all the talks that I've seen here, and I'm looking forward to a lot of great talks coming up. And also, happy Octoberfest, everybody. I hope you've all got a nice glass of something next to you. I've got my 2 beer right here with me. But yeah, so it's a nice way to you know, spend our time as category theorists, obviously. So for my contribution to this little event, I wanted to tell you about a construction that I've been working on for several months now, and it's in an advanced draft, I might call it. It should be on the archive this week or the next. It's a construction of the homotopy bicategory of a complete twofold Segal space. I will explain what all that is in a moment. All right. So, higher category theory is a bit of a pain. I don't think that's any news to anybody. A lot of constructions that we think should be very sort of straightforward and should just work are actually a much more non-trivial than we realize once we start looking at the details. So, for example, if I give you an infinity n category, you should just be able to get a weak n category out of this by collapsing all the n morphisms that have paths between them, right? If you can take path components of n morphisms, given an infinity n category, you should just get an n category. You should just be able to take the homotopy n category of an infinity n category, right? No, not as simple as you might think, because unfortunately, there's a lot of complexity in what this means and in what this means. So, for instance, if we think of some very popular models of infinity n category, for example, complete n-fold Segal spaces, which in the case n equals 1, these were devised by Resk, and Barwick extended them to general n in his thesis. The problem is that these models and things like them, they can be very different from our model of n category here. For example, suppose n equals 2, and we're trying to go to bicategories. In a bicategory, if you have a bunch of morphisms and you want to compose them, there is just the composite, given you've chosen bracketings and such, right? There's the composite. And if you have different composites, like for different bracketings, you've got the associator, and you've got a pentagon condition, right? There's all this algebraic data. It's an algebraic definition in some sense. But a complete n-fold Segal space, or a twofold Segal space, is nothing like that. There are no composition operations. Instead, what you're given some things you want to compose, you're given a space of possible composites. And this space is contractible. So you have a range of options, and they're all the same. So that's a nice way to avoid having to write down the coherence conditions. But once you go to an algebraic definition, you got to write them down anyway, right? The pain's got to happen somewhere, right? So, but in my opinion, this is a good pain. It's a growing pain for higher category theory. It's by solving this problem of going from some non-algebraic notion of higher category to an algebraic one along a construction like this, we'll learn more about both aspects, both notions of higher category, see where the structure in one way comes from the other and vice versa. So that's what I want to talk to you about today. I want to tell you a little story about how to take the homotopy bicategory of an infinity 2 category, a complete twofold Segal space, the kinds of challenges that come up when we do this in inducing algebraic structure from non-algebraic. So today, we're going to look at the cases of this diagram of n equals 1 first to get some idea of how things work, because this is a very well understood case. This was originally due to Resk for our specific definition of infinity n category. And then we're going to extend those ideas to n equals 2. So when we want to generalize some construction, often we need to rephrase it in some way, because often the original statement was not made with extension to generality in mind, so we have to change perspective and rephrase things a little bit. So the original construction that, that's the wrong color. The original construction that Resk gave, I'm going to give it in a slightly different way. Okay, so let's start with a theorem. So Duderesque, but sort of slightly rewritten and permuted. So given an infinity one category, which is for us a complete Segal space, for now, all you need to know is that a complete Segal space is a simplicial set satisfying some properties, and we will say what those properties are as we need them. So given a complete Segal space, an infinity one category, the following data will specify a category. We'll specify a category, or specifies a category, I should say. And this category we will write as H1 of X, the homotopy 1 category of X. Hn would be the homotopy n category. Okay, so what is this data? Well, imagine we took an infinity one category. We wanted to collapse it down. To a category by taking path components of one morphisms. What would the objects of that category be? Well, they'd just be the same objects again, right? Nothing's changed. So the objects are exactly the same as before. They are just the objects of our infinity one category, which is this set. All right, the intuitions for why these things are what they are will become more obvious as we go on. So for Hom sets now, things get a little bit more interesting. So we want the path components of one morphisms, right? So let's think about this diagram. So x1, the image of 1 in delta, this thing we should interpret as the set of the space of one morphisms in our infinity one category. And we have an induced map to x0 times x0, which we should think of as the space of pairs of objects in our infinity one category. And all this map is doing is just forgetting the morphism. It just gives you the source and target. That's it. Now, there's an obvious inclusion here of our two objects that we have in mind. And all we do, just take a pullback. So we get the space, we take the fiber, right, over two objects, and we get the space of morphisms from X to Y. Easy enough. Now, if we want, we just take path components of this, right? This is a simplicial set. We can apply pi zero to it. And for those who might be a bit worried about pi zero of a general simplicial set, X of xy is a con complex. It's always a con complex. So there's always just, there's no like zigzags of paths that we have to worry about. It is very computable. Okay, so we have Hom sets now. And identities are very simple. We just think about the degeneracy map, right? And this thing, it takes an object and gives us a morphism, which we think of as the identity morphism, and we just fiber this over X. And this gives us a map of this form, and apply pi zero, and we get our identity element. Now, all of this thus far has been pretty much exactly the way that it originally is written. And, you know, the way you see it, might see it in Resk or Johnson-Frade and Scheinbauer or Kallick and Scheinbauer's work when they use complete n-fold Segal spaces. Very classical. This is the bit where things are going to get a little bit different. Because now I'm going to write composition in a slightly different way. Usually, okay, it's not too interesting to think about what it does. Usually, just think about this new way. So I'm going to show you an interesting diagram. Consider this space. What is this space? Well, it's the space of a morphism and another morphism that agree on the source and target. It's the space of chains of length 2 in our infinity 1 category. Let's look at the identity map. And now let's look at the space x2. x2 we should think of as the space of chains of length 2 together with a chosen composite, right? And we get a natural map induced by the simplicial structure, which basically just forgets the composite, just gives us the two morphisms. I mentioned before a contractible space of composites. What I mean by that is pick an element in here and look at its fiber, right? That fiber will be the space of composites. Okay. There is then another map here to x1, which just takes the underlying one morphism, right? Now, this is actually a lifting problem, because one of the conditions on a complete Segal space is this has to be a trivial fibration. That is a condition. That is part of the definition of a complete Segal space. And because this is a trivial fibration and everything's cofibrant, this is a lifting problem. And so we can solve it. I know that's a little bit too rainbowy and colorful for, you know, it's not Pride Month, but every month is Pride Month, so whatever. This we can solve. We get a map mu2, and what is this doing? It takes a chain of length 2, and it picks a composite. Perfect. We picked a section of a trivial fibration, right? It's like a section of a fiber bundle. Okay, and we have this map, and if we fiber it over objects in a nice way, we can get for any objects x, y, and z, that we get an induced map to x, x, z, right? Where this thing is the fiber here, and this thing we fibered over x, y, and z, right? Okay, now, we just hit this thing with pi 0. And because pi 0 commutes with products, voila, we have our composition operation. Yz to of xz. Perfect. All right. So we have all the data of a category. Now we need to prove the coherence conditions. We need to prove associativity, for instance. Now, I'm only going to talk about associativity today. I'm not going to talk about identities. It's a similar story. The sort of the yoga that we do with the associativity is going to be similar for identities. If you're interested, you know, I mean, maybe that's for a future discussion. But I'm just going to talk about associativity today. Okay, so let's prove associativity. So how do we do this? Okay. I'm going to draw a slightly bigger diagram. So what we want to prove is that HEF is equal to HGF in our homotopy category. Let's think about these two composition operations. We can write them in a bit of an interesting way. Let's start with chains of length 3 this time. And then we have the identity and chains of length 3. Right? So this thing is chains of length 3 in our infinity 1 category. Now, there are some interesting spaces that live above this thing. And the first one is a space that we can construct out of pullbacks of x2s and x1s in a very obvious way. I mean, it's not difficult at all. It's going to be the space that I'm going to write like this. And what this is just a pullback of x2s and x1s such they agree on certain boundaries. You can do this in your sleep. It's a space whose diagrams are chains of length 3 together with a choice of composite of the first two morphisms and then a choice of composite of that with the last morphism. And that's it, right? And we have an evident map. So we have x1 living way over here in the corner. And we have a map from that to x1, which just gives us the bottom morphism. And just like this thing is designed as a pullback of x2s, similarly, the mu2s that we wrote down, we can take a pullback of those to get another map up here, right? Take a pullback of our mu2s and we get an induced map up to here, right? And what this does is it takes a chain of length 3 here, and it uses mu2 to pick a composite, and then uses mu2 again to pick another composite. So if you unwind this pullback, you find that this is literally the composition operation specified here. It's just literally equal to that composition operation. So that's our first composition operation. This path here is our first composition operation. It's the same as this. So what about the other one? We get a very similar story. We have another space, which is the space of diagrams this time of this shape, which is just a different kind of pullback. We get a map down here that just forgets everything other than the spine, or the chain of length 3, you can call that the spine. And again, our mu2s induce a map here. What we should think about this space as is chains of length 3, a composite of the last two morphisms, and then a composite of that with the first morphism. And if you look at the forgetful map from this to here, this path here is literally just equal to this, right? Just unwind the pullbacks, and that it is that. So we have these two maps. So how are we going to compare them to each other? It seems like I've made things more complicated than they need to be. But actually, there's quite an interesting thing that happens, because let's look now at x3, the space of tetrahedra in our infinity 1 category. That sounds like a bit much to be thinking about, but we can just think about some of the data that comes with a tetrahedron. What that would be is a diagram with a chain of length 3, a composite of the first morphism, the composite of that with the last morphism, and then on top of that, also a composite of the last 2 morphisms, and then a composite of that with the first one, such that the composites agree, right? This is just the data that we imagine X3 represents. Now, there are induced maps here and here, which just forget the back face or the front face of the tetrahedron. And there's also a map here, which just forgets everything other than the spine. And these 3 maps commute with one another. It's, I mean, you know, forgetting information about the tetrahedron in any order, I mean, it's all the same, right? So these 3 maps all commute with each other. Now, why did I bother with that? The interesting thing is that this map has to be a trivial fibration by the properties of a complete Segal space. So does this. And so what we have is actually this forms a lifting problem, and this forms a lifting problem. The problem of, So what we can do is we can solve this first lifting problem. So we get some solution here. And we can also solve this other lifting problem. And we get another solution way over here. And if we look at the map that brings us down to x1, actually what we find is, so this was one of our composition operations, right? Well, this thing has to commute with this thing by the definition of our lifting problem. That's one of the requirements of, commutativity for the lifting problem, right? And that has to be the same as this. So actually, this operation is just this path. And moreover, this operation, in the same way, is just this path. So what I've done in the end of all of this, lifting problem kung fu, I'm going to reduce this. I'm going to chop out a lot of this picture, and I'm just going to have some of the underlying information. So we have our chains of length 3. I'm just going to look at x3. We're going to forget about these 2 other spaces. We have a map to x1. And what we've induced, this is also a lifting problem because this has to be a trivial fibration. And what we've induced is 2 solutions to this lifting problem. And each of these paths corresponds to each of the bracketings, right? If you fibered each of these over your objects, you would literally get composed nested on the left or composed nested on the right by all the commutativity from before. So we've repackaged the problem of equating these 2 things with equating these 2 paths. Now, here's the thing. It's classical in a model category, in any model category that you like, that if you have 2 solutions to the same lifting problem, there is a homotopy between them, always. And you can do this by turning your lifting problem with these solutions into a new lifting problem. Any solution of that is a homotopy between these 2 solutions, right? So what we get is, once we take fibers over our objects, we get, not homs, but so x of xy times x of yz times x of z w. I definitely know the alphabet. We get, for our 2 composition operations, xw, which are just these 2 paths, right, fibered over objects, we now have a homotopy induced between them. Our homotopy is necessarily fibered over objects, by the way. That is another property that you can prove with these things. So we genuinely get these homotopies. Now, here's the thing. Pi0 will send homotopies to equalities. What is a homotopy but a parametrized path? It's a big path, right? And pi0 turns paths into equalities. So pi0 will turn this homotopy into an equality between these 2 composition operations, right? And that proves associativity, right? Because when you apply pi0 to this picture, what you get is you get your first composition operation up here, and then you get your second composition on here, and this thing becomes an equality. And that proves associativity. And because we're not discussing units, That's definitely a category, right? Great. So that's the story for n equals 1, which is really not news at all. But the interesting thing about this telling of the tale is that actually, when we step to n equals 2, I really don't need to write very much. I don't need more slides. I can just go all the way back up here and edit very slightly everything that I've written thus far to cover infinity 2 categories, because this construction will generalize. So how does it generalize? Okay, well, this time, given instead of, okay, so first off, maybe I should say, res, get out of the way. It's R now. So given now, instead of an infinity 1 category, an infinity 2 category, so sorry, a complete twofold Segal space. A complete twofold Segal space is just a certain bisimplicial set satisfying some properties, which we will come to later. The following data will now specify a bicategory H2 of X. So first off, take an infinity 2 category, collapse its two morphisms down. What are the objects? They're exactly the same. So we just take the underlying set of objects, right? Now, for Homs, instead of Hom sets, we want Hom categories, which I'll just capitalize the H to signify. So this whole diagram is now a diagram of simplicial spaces, right? Because everything's stepped up a level now, right? We originally had a map from delta 0 to simplicial sets. Now it's a map from delta 0 to delta 0 to simplicial sets, right? So this is now a diagram in simplicial spaces. And we can just do this pullback. And actually, everything in this picture, all of these four things are complete Segal spaces. That's one of the conditions on a complete twofold Segal space, right? All of these spaces have to be valid infinity 1 categories. So this thing is a complete Segal space, which means that we can just apply H1 to it. We can take the homotopy category of morphisms from X to Y, whose objects are 1 morphisms and whose 2 morphisms are path components of 2 morphisms from 1 morphism to another, right? It's exactly the interpretation that we want. And this thing, nothing changes, exactly the same, right? I mean, we apply H1 here, but whatever, it's the same. Now, composition, I haven't written pi 0 anywhere on the screen here, right? We can do exactly the same story. We have our infinity 1 category of chains of length 2 and a chosen composite, right? We have chains of length 2, chains of length 2, right? And this is a valid lifting problem. One of the conditions for a complete twofold Segal space is this has to be a trivial fibration in some sensible model structure on complete Segal spaces, right? Everything is cofibrant. And so this is a lifting problem. And so we can still get mu2, right? We can still choose this lift. We can choose for any chain of length 2, a composite, right? And so now, fibering over objects, we get a map this time of infinity 1 categories, right? The infinity 1 categories of morphisms going to infinity 1 category of morphisms. And now, instead of applying pi 0, we apply H1. And we get our composition functor. Nothing has really changed. Now things change. So this whole diagram, so now instead of proving associativity, we want to construct an associator that satisfies the pentagon condition, right? So this is our new challenge. We don't want to prove equality here. We want to construct an isomorphism, yeah? So how do we do that? Well, everything that I've drawn here is fine, right? All of this still works. What this reduces to is saying that, well, my 2 composition operations that I'm interested in, I can rephrase them as 2 solutions to the same lifting problem, right? I can still do that. And still, there must be a homotopy between them. Nothing's changed. It's a general model category theory fact. There must be a homotopy here. Now, we get this exact same picture, this time in infinity 1 categories, yeah? But now we're not applying pi 0 anymore. We're applying H1. And H1, if you set things up nicely, will send a homotopy to a natural isomorphism. And so we get an associator induced. So at this stage, I'm not really allowed to complete the proof because, that'd be a bit pathetic. I haven't even proved the pentagon condition, right? So how do we go about thinking about the pentagon condition? Well, I'm not going to write everything out right now, but what I will say is this. Take a look at this diagram. We can do this diagram again, except with chains of length 4 now, and going up to x4, right? And looking at spaces within this, right? Basically what we wind up with is that there are 5 different diagrams corresponding to the vertices of the pentagon, and then 3 cells above them corresponding to the edges of the pentagon, right? And what we wind up with, if we compose all of the homotopies we get between these, we wind up with this lifting problem. So let's look at chains of length 4 now. Same thing here. And now we have x4 living up here and a map to x1. And we get, 5 solutions to this, but we'll only think about 2 of them. The first one being, so what's a word? I guess K, H, G, F. I know the alphabet. And so one of these corresponds to bracketing all the way on one side, and the other one corresponds to bracketing all the way on the other side. Yeah? And by following the paths of homotopies we get between all the different composition operations, we wind up with 2 homotopies, yeah? Corresponding to, in our pentagon, this path and this path, right? Composing all of our homotopies that we got, which induced our associators. Now, here's the thing. These 2 homotopies, I told you before that to get a homotopy between 2 solutions to a lifting problem, you construct a new lifting problem whose solutions are the homotopies you seek. These 2 homotopies are solutions to the same lifting problem, which means there must be a homotopy between them, a homotopy of homotopies, right? A 2 homotopy. And this 2 homotopy, moreover, can be made to be globular. It can be made constant on the endpoints, right? And here's the final fun kicker. H1 will send globular 2 homotopies to equalities. It's a level up. It just reduces to pi 0. You turn homotopies into equalities. And so what that means is that the path of associators induced here and the path of associators induced here must be sent to the same natural isomorphism because there exists a 2 homotopy between them. And that proves the pentagon condition. So we have a bicategory. Now, I've ended a little bit earlier than I expected I would, which is a good thing. So I might say a few words about how this construction really works, because I will admit I have deceived you slightly. In reality, what this construction actually is in the paper that I've written, we have a functor, H2, going from complete twofold complete Segal spaces, complete twofold Segal spaces, not to bicategories. We instead chose to go to unbiased bicategories. These were defined by Leinster originally, I believe. The reason we do that is because unbiased bicategories. So an unbiased bicategory is like a bicategory, but you have n array composition for all n. You can compose like 5 morphisms at once if you wanted to, right? It's like an unbiased monodal category. And the reason we chose this is because a complete twofold Segal space looks quite unbiased. You actually have like lifting problems for all n, right? So x1, and like the same thing here. These are all possible lifting problems. And so it feels like there should be unbiased composition, right? So to offer more flexibility, we went to unbiased bicategories instead. And moreover, so I never tell you about pseudofunctors. This does work with pseudofunctors. We have shown that you can send a map of complete twofold Segal spaces to a pseudofunctor. And however, this isn't quite the category that we start with. Instead, we have complete twofold Segal spaces. I just read comp here, that's my notation. For a complete twofold Segal space decorated with a choice of the solution to the lifting problems, right? Because different solutions to these, we chose these maps mu2, right? And different choices will give different composition functors. Because remember, in a complete twofold Segal space, we have a choice of composites, it's contractible. We're making a choice of which composition we choose, right? However, that choice is actually quite irrelevant. If you have 2 choices, mu2 and mu2 prime, we also show by this functoriality that there must be a pseudo-functor induced between these, which is the identity on objects, morphisms, and two morphisms. And as a matter of fact, it's the unique functor that comes from this, right? The unique pseudo-functor that comes from this, that it comes from just from the identity. So there is choice, but there's not much choice. There's a contractible amount of choice, which is exactly what we expect. Contractibility stays contractibility. And I think that I'll end on that little strange philosophical phrase. So thank you very much for listening, everybody.
Let's thank Jack again with our virtual claps.
I'll take it.
Are there questions? I see one question in the chat. Judith, do you want to ask further about that?
Okay. First of all, like, that was a great talk. Thanks.
Yes.
Yeah. So my question was about the first case, the complete Segal spaces. I think you mentioned at one point that something you were doing was different in the way you define compositions. Could you maybe speak a little bit about that?
I mean, all I'm saying is that, like, so in Rezk's original work, and when you look at like Johnson Freid, Clark, and Scheinbauer's like writings on this, usually what they'll say is that the Segal map, it's a weak equivalence, and so it gets sent to a bijection, and so we just take an inverse of this, which is the same, really, at the end of the day. You know, I mean, we're picking a specific inverse. I mean, at the end of the day, nothing changes really. It's just a different interpretation. Like, yeah.
I think I learned about this from like Nima Rasek's notes. So I like that seemed very similar to what I'd read. So I was like wondering what's different.
I've not read Nima's notes, so like maybe I should have a look at that at some point. Maybe like, I mean, yeah. This is not like a deep reinterpretation or anything. I suspect it's been thought about before, but it's different from what Resk wrote originally, I guess. That's all I would say.
Yeah. I guess the other natural question is this generalized to higher like n? Like you go from 1 to 2, can you go from 2 to 3? But
coming soon to a theater near you. This is so the thing is that what's really nice about this construction actually for unbiased bicategories is it's really operatic. So these sorts of diagrams that I drew before, you can basically define an operand valued in cat of these, and in this like this operation basically looks exactly like an action of this operand on like the operand of like Hom, like colored operand of like Hom categories and like pseudo functors between and like functors between them. Like the theorems look exactly like an operand. I don't state that explicitly, but I hope to very soon. And what this suggests to me, there's sort of this thing where we're going from a trivial fibration to an action of an operand that seems like quite general. And I have a cookbook recipe now for how to go from a complete n-fold Segal space to, say, a Trimble n category. It induces an action of an associahedron inductively. That will be near future work. Yeah, so it should work for general n. That's the goal. But yeah, so great question.
Looking forward to see that. Thanks again.
Yeah, thank you.
Brandon, want to go next? Ask a question.
Hey, Jack. Thanks for a great talk.
Thanks.
Got a couple of questions about model choices.
Sure.
So, first one, have you thought at all about the Tamsamani model for weekend categories? Because I asked just because they both seem very simplicial.
It's totally a great question, and I know that Simona strongly suspects a connection between complete n-fold Segal spaces and like Tamsamani and categories. The one thing I have to say about that, which is like the main reason I didn't go to them right now, is because really like they have this sort of constancy condition at like level 0. Which looks a lot more like a Segal n category, in my opinion. And there's no like immediate, really natural way, just like, post-compose with like path components or something like to get to, or like with H1 or something to get to these. And the thing is as well that like the passage from complete n-fold Segal spaces to Segal n categories, that's a right adjoint, like the most natural one. And you want H2 to be like a left adjoint. Like really, we want like a nerve homotopy n category adjunction. Usually homotopy n category should be a left adjoint. I mean, maybe there is like a sort of neat way of doing it, but Segal and categories would be the more natural place to start if you wanted to go through those. I would like to do that at some point, but you know, yeah. Also, we wanted like a really concrete construction. That was like part of our sort of motivation to do this. Like we want to apply this to specific things. Yeah. So, but yeah, it should work. your suggestion at some point.
My other question was, so I believe I saw a construction of a homotopy bicategory for a 2 quasi-category.
Yes, Campbell. Yeah.
Yeah. Does that connect to this, or are your techniques related, or?
Yeah. So first off, really sorry that I didn't give many references like in this talk. I really should have, but I was writing by hand, and so I can like send notes or something later, like with references. But yeah, so Campbell like has done that. He defined a nerve to these, and then like I think what he says is that then you have an adjoint going down to Tamsamani 2 categories, and then these like Lack and Paoli's work then takes these 2 sort of bicategories. The thing is like that works. But I want to really specifically like know where associators come from and things like that, and like where the composition comes from and how to choose all these things. Campbell's work to me sort of strikes me more as like a universal kind of construction, if that makes sense. Like I'm sure you could go through all the motions with it, but like I'm sure they're related. If you pass through some equivalence from one to the other, maybe they'll commute or something like that up to equivalence. But yeah, I've not done it fully though. So
Cool. Well, thanks again.
Simon, you had your hand up. Did you want to ask a question still?
I had a question, but I think the last answer kind of answered it, so I'm good. Wait.
Okay, then I'm calling the break.
Okay, all right.
Let's thank Jack again.
The recording has stopped.
And so since we are starting late with our break, Rick, what do you recommend?
Let's see, we were supposed to restart at 3:45. You want to just say 4?
Sounds good to me. So, okay, so we give, there's still a roughly 22-minute break, and we'll start again at the hour, wherever you are.
All right. And of course, if people have other questions, my email address is up here. I'm very happy. I really want to hear what people have to say. So like.
Yeah, I really like this talk. If you have further notes, I would love to see them actually.
Sure.
So, is any of this already written up, or is this just work in progress?
The paper is basically done at this point. I mean, it should be on the archive like this week or next. But yeah, it's just little bits of proofreading I want to do. I don't, please no typos, and stuff like that.
Don't forget that.
Yeah. So no, very soon now. Hopefully.
Okay, then I'll have a look at it later. You've got some more questions by email.
Awesome. Great.